So this is our second lecture on ergodic theory, and we're going to focus now on ergodic measures. So what we talked about in the first class was stationary measures, and now we're going to talk about ergodic measures. So this again is kind of a probabilistic notation for the subject we are dealing with. So before, we have to introduce the definition of invariant events. So imagine that we have phi that goes from some space S to S, and some set A that is measurable with respect to S. We're gonna assume Borel sigma algebra for now, but it could be anything. So we say that A is invariant with respect to phi if phi minus 1 of A is equal to A. So this is the rigorous definition, although we are not going to follow the definition below, but in several situations some theorems could be modified to include an alternative definition. Where we have some probability P that you see the above definition has no probability P. So here, no probability. But in this alternative definition we have a probability P, and we just say that A symmetric difference with phi minus 1 of A has probability 0. So this is an alternative definition that some people use, and sometimes it's useful to use this definition. But since we like the definition that doesn't have a probability, we're going to keep the black one. I'm going to forget the purple one. But it's always good to know that this is also a definition, and in some cases this definition make your life easier. It's almost like almost sure invariance instead of true invariance. But we're not going to use this really. And as before, after introducing something, let's give several examples. So examples, of course there is always example 0. If A is the empty set, phi minus 1 of the empty set is the empty set. Or if A is a whole space, then we're done. Phi minus 1 of the whole space is the whole space. This is trivial. Now let's give some non-trivial examples, and for this we're going to need some specific S. And the S that we're going to take is R to the N. So it's just a space of x1, x2, and so on. Space of sequences, real sequences of real numbers. So the type of event, again we have this xi, the canonical coordinates. Not going to define them again, but they're just taking this sequence and return the ith coordinate. So what are the type of invariant events we can come up with? So A, for example, could be the limit in K of xk exists. So this is something that if it happens for the sequence x1, x2, and so on, and we shift this sequence, and phi here is the shift. Forgot to say what phi is. So if phi is the shift, we just shift the sequence. The fact that the limit exists cannot change. If it exists here, it will also exist here, and vice versa. So this is invariant with respect to phi. Also, the limit being equal to something, this is also invariant. If we shift, we cannot change the limit. And there are several examples like this. Lim sup in k of xk is finite. This is also an example. If you shift, you cannot make the limit to become finite because of that. There are some less trivial examples, although it's easy still to prove, but the limit in k of 1 over k, the sum for I equals 1 to k of xi exists. So the C0 limit of xi existing is also something invariant. This is slightly less trivial to prove, because you cannot just pick the definition, you have to prove something. But the fact that k plus 1 over k converts to 1 essentially gives you what we want. So this is an exercise. So these are some examples of events that are invariant with respect to the shift in this standard space. Now that we have the definition of invariant events and some examples in mind, we can finally talk about what it means for a measure to be ergodic. Now it's where we are introducing measures. So we say that P is ergodic. So here, with respect to phi, which goes from the space where P is defined to itself, if for every A that is phi invariant, the probability of A is either 0 or 1. So this is just the definition. This is going to turn out to be extremely important in several examples we're going to talk, and real world applications in statistical mechanics, in dynamical systems. This is a very, very important definition. We're going to use this definition as hypothesis for very important theorems that have very important physical interpretations. But before, let us just give the most physical interpretation of this definition that I can imagine. Right? So it comes from negating this definition. What happens if P is not ergodic? So let's just take the definition and negate it. Then there exists an A, right? Invariant with respect to phi and with the probability of A between 0 and 1 strictly. So here this definition this is just the negation of the definition. There's nothing here, but we're going to give an interpretation to this situation. So we have here our set S, we have a function phi, goes to S again, and if we restrict phi to A, let's imagine, of course, a phi can be thought as applying to A, so A is a subset here. We can apply phi to A, and the fact that it's invariant means that we can take the pre-image of A, and it's going to be in A itself. So there is something here that is going to A. Actually, everything here is going to A. Everything that ends up in A is in A. So this is invariant with respect to phi. And what happens to the complement of A? So let us look. We know that phi minus 1 of A is A. meaning if something ends up in A, it was in A. So if something ends up outside of A, then it was not in A. So pre-images are well behaved with complements. That's why you can define the pullback. So this means that the A complement is also invariant. So if you end up in A complement, of course you do not end up in A, so you're not here, so you're not here, so you are in A complement. And if you are in A complement, you're not here, so you don't end up in A, so you end up in A complement. So these two are equalities. So that means that this, so to say, dynamical system phi can be decomposed into simpler systems that don't interact with each other. Can always think like this is phi 1 and this is phi 2. So if something is not ergodic, you can split your space into two components that don't interact with each other. So that means you started studying a system that is not as simple as it could be. So let's give an analogy in geometry. You can usually suppose in your geometry theorems that a manifold is connected, because if it's not connected, you can decompose it into two components, into connected components, and you can study each connected component separately. So this ergodic decomposition is not what we are claiming here. This is a theorem that we can prove, but what we are saying here is that, okay, if it's not ergodic, it means that you can at least split into two, and more importantly, the fact that probability of A belongs to 0, 1 implies that the probability of A complement also belongs to 0, 1. So this, you decompose the space in a non-trivial way. There is positive mass here and there is positive mass here. Of course, if you could decompose but one of them had measure 0, this would not be an essential decomposition. So another way to state that something is ergodic is to say that you cannot split S into non-trivial and non-interacting components. Everything in S is interacting with everything else in S. Okay, but now the question is like, is there such a thing? Does this exist at all? So what we're going to give now are some examples of ergodic things. So let's keep the tradition of giving first example 0. If S is A, then phi has to be the identity, and any probability measure has to be delta of A, and this is ergodic. So this is kind of silly, because every event is invariant, but also every event has probability 0 or 1. So this is example 0. A much more interesting example that we are actually going to have to prove something here is the infinite product with the shift. So let's imagine that we have omega being S to the n. So we take any metric space, take a product, and consider phi to be the shift here. And of course you have the canonical coordinates and so on. We fix mu, a probability, on S, and let P be equal to the infinite product of mu. So we're going to prove that this is ergodic with respect to the shift. So P is ergodic with respect to the shift. This is going to be a theorem. So how do we prove that something is ergodic with respect to something else? So we first go back to the definition. We need to take an event A, an arbitrary event that is invariant with respect to phi. So take A, an event here that is phi invariant. Okay, one way to write A, which is very silly, is A is equal to, so to say, omega belongs to A. So all the omega. So what's this notation, right? This notation is all the omegas such that omega belongs to A. Of course, this is true, and this is a notation that we use for this, right? This bracket. But what is omega? Little omega is a product, and it can be written in terms of the canonical coordinates. x0, x1, and so on belongs to A. Now remember that A is invariant with respect to the shift. So that means that this is the event here is exactly equal to the event x1, x2, so on belongs to A. It didn't change the event. And we can even repeat this many times until we get to the point that we can say xk, xk plus 1, and so on, belongs to A. So it seems like we did nothing here, but we just wrote A in a strange way that essentially tells you that A belongs to the sigma algebra Fn. Fn is defined as sigma algebra generated by xk, xk plus 1, exactly what we have above there. So why are we doing this? I'm just saying if an event is invariant with respect to the shift, it's measurable with respect to the sigma algebra Fn, no matter the n. Sorry, should be Fk here. Sorry. And this is A belongs to Fn, Fk for every k. What does that mean? This we saw in probability 1. This is the definition of A being a tail event. Now tail events on product spaces have probability 0 or 1. This is the 0-1 law for tail events. So we use the 0-1 law for tail events on product spaces, and we just proved, we use this to prove that product measures are ergodic with respect to the shift. So now we're gonna, of course, talk a little bit about what we're going to talk about in the other classes. What are the consequences of something being ergodic? So if you know this, then you know A, B, C. We are going to give several implications of something being ergodic. But this is usually a lot of statements that you know already for product measures. So the product measure is an important example of ergodic measures, but they are not the most important, because everything you can prove for ergodic measures is kind of trivial for the product measure. So what we're going to do now is just give a few other examples of ergodic measures that are not products, so that you understand why we are interested in giving results that hold for ergodic measures as a hypothesis. So we're going to give more examples. Example 2 is actually going to be a counterexample. So suppose that our space S is S1, the circle. This is just a set of pairs such that x squared plus y squared is 1. So this is just the circle, and we're going to define phi, of course, and phi is going to take e to the theta x, any point in the circle can be, I theta x, any point in the circle can be written as such, and it's going to take it to e to the I, e to the ix is the point in the circle, and it's going to take to e to the ix plus theta. So what is this function here, this dynamical system? It's rotating the circle by an angle of theta. So this is what this application is going to perform. It's going to rotate every point by an angle of theta. And in example 2, we're going to suppose that theta, so actually there should be a theta here. We're going to suppose that theta over 2 pi is rational. Okay, so for example, theta could be 2 pi over 3, and if you divide it by 2 pi, it's 1/3, it's irrational. So what we can prove in this case, of course we need a measure, is that the measure, which is the Lebesgue measure, on S1 is not ergodic. So let's try to give an intuition of what's going on here. Let's take the example theta is 2 pi over 3. Okay, so we have here the circle, and phi is going to send this point to this point. This point is going to be sent to this point and back to 1. What if we define the set A to be this? It divides the circle not in 3 as in the denominator here, but in 6. Okay, now we have the circle divided into equal pieces of size 6, and A is going to have this first interval here, this interval here, and this interval here. So A is a union of 3 intervals. What happens when we apply phi to A? This is going to give A. It's going to rotate this point to this point, this to this, and all the intervals are going to be sent to the next interval, and all the holes are going to be sent to the next holes. Actually, phi is a bijection. So A is invariant with respect to phi. But what is the Lebesgue measure of A? It's 1/2, which is of course not in 0, 1. So this second example is an example of measure P which is not ergodic with respect to this rotation. And of course we could also phrase this in the shift case. We could take a P prime, for example, to be P gamma minus 1 of phi, and this will be a measure, a probability measure, right, on S1 n, and this is not going to be invariant with respect to the shift. So not be ergodic with respect to the shift. It is invariant, but it's not ergodic. So here you can also prove that this is invariant, that the rotation is invariant with respect to the Lebesgue measure. This is essentially just a consequence of the Lebesgue measure being invariant with respect to translations, but not ergodic. Now the third example that we're going to give is going to be on the same setup. P is Lebesgue measure on S1, and we're going to consider phi theta just defined as above for theta such that theta over 2 pi is irrational. So in this case things are going to change a lot. It's kind of counterintuitive, but after it's a bit counterintuitive that this notion of ergodicity is so sensible, right? Rational numbers and irrational numbers are so intertwined that it's kind of a strange notion to know that this being ergodic is not an open property with respect to theta. You change a little bit theta and you can change completely if the application was ergodic or not. So it is what it is. This is ergodic with respect to P. And here I'm again using the dynamical system notation, right? The function is ergodic with respect to measure. Usually probabilists who say the measure with respect is ergodic with respect to the shift. Okay, so how do we prove this? The proof is going to use a bit of previous technology. So if you didn't previously know it, it's not that complicated of a technology that we're going to use, but anyway. So what we have to do now is way more complicated. So see, proving that something is ergodic is much harder. Let's see why. Because we're having to prove that something holds for every A. If you're proving that something is not ergodic, you just have to show an example. So since we have to show it for every A, it's going to be harder. So given any A, that's a Borelian set of S1, we're going to define, we're going to write A as a function, right, the indicator of A, and what you're able to do is to write this in a Fourier transform. Why are we writing this in a Fourier transform? Or the Fourier series if you prefer. I mean, we're talking about shifts, rotations of the circle, and we know that the basis of the Fourier transform behaves very well with respect to rotations of the circle. Actually, we even started, when we started talking about this, we even started denoting points with this, of the circle in this notation of the exponential, the complex exponential. So it's not completely unintuitive to decompose this into a Fourier series. So we're going to sum from k from minus infinity to infinity. We have some coefficients ck. They're going to multiply 2 pi I kx. So this is just to make the coefficients in radians. This is the complex because we're taking Fourier transform. This is the parameter that we're summing, and then we have function of x. So this is the canonical Fourier series decomposition. And what this says is that the series on the right converges in L2. So it's actually quite a good convergence. So this is not an equality almost surely. This is not an equality in every point. It's something that holds almost surely, and it's a convergence in L2. Now, what does it mean for A to be invariant? Right, so phi theta invariant. So A invariant gives, let's write it in terms of the decomposition. It means that indicator of A of x, this function, is equal to indicator of A of x plus theta. That's what the phi is going to do. Phi is going to be applied to x before looking if you are in A or not. So if we use the decomposition, this is the sum k of ck e to the minus 2 pi I kx, and this is just the same decomposition but looked into a different x. Okay, and of course here the exponential of a product of a sum we can just turn into a product, so e to the minus 2 pi I theta is going out of the sum. I'm not even going to put it out of the sum, I'm going to write it like this, it's more convenient. ck, sorry, there's a k missing here, and now e to the minus 2 pi I kx, which is exactly what we had before. So what I'm saying is that this sum here is equal to this sum here, and these two sums are Fourier decompositions of the same function. So by the uniqueness of the Fourier coefficients, we have that ck is equal to e to the minus 2 pi k ik theta ck for every k. Okay, so this is the essence of the proof in terms of the technology that we are using. We are using the Fourier decomposition to be able to write this, and we are using the uniqueness of the Fourier coefficients to be able to write the equality below. But now we can forget Fourier, now it's just algebra. What this says is that ck times 1 minus this exponential is equal to 0 for every k. Of course, what is in the right here, it's very explicit. We don't know what ck is, but what's in the right is very explicit. This thing here is equal to 1 if and only if k theta is an integer, right? Only in multiples of 2 pi I the exponential is going to be 1. So this, since theta is irrational, so now we are using the hypothesis that theta is irrational, only happens if k equals 0. So we know that this is going to be 1 only when k equals 0. So otherwise this is going to be different from 0. So the only reason why the product is 0 is because ck is 0. So ck is 0 if k is different from 0. Because if k is different from 0, this is not an integer, this is not 1, this is not 0, so ck has to be 0. So what does it mean? Let's look at the decomposition again. This is a sum of ck's, but all of them are 0 except for the 0. E to the 2 pi I times 0 times x, but this is just 1. So this is going to be C0 almost surely, right? The decomposition is an L2 decomposition. It only holds almost surely. But we're essentially saying that the indicator function of a is a constant almost surely. So an indicator is 0 sometimes and it's 1 sometimes. If it's a constant almost surely, so a has to be equal to the empty set almost surely. So probability of a symmetric difference with the empty set is 0, or a is the whole space almost surely. In this case the probability of a is 0. In this case the probability of a complement is 0. Oh, sorry, yeah. Because the symmetric difference with the empty set is just the set itself. The symmetric difference with the whole space is the complement. So in any case, P of A belongs to 0, 1. So we have worked a bit hard but we proved a very interesting result from the dynamical systems perspective. If you take rotations on S1, they're going to be ergodic if and only if the rotation is rational. So as a last example, so that we can't say that we are not familiar with ergodicity, I'm going to give another dynamical system, this time on the 0, 1 interval. So this is going to be our S. Okay, what is our probability here? P is going to be just a uniform 0, 1. And what is phi? So phi is going to have a strange looking face. So phi is going from S to S as usual. It's going to take a little x and take it to 2x minus the integer part of 2x. So before you start to scratch your head about what this looks like, let's draw a picture. So here between 0 and 1, and at 0 we have 0 minus 0, so it's 0 here. This is going to be 0 until x hits 1/2. So until 1/2 we don't have to care about this, it's only 2x. So it's gonna get close to the value 1 here when you get close to 1/2. But when you hit 1/2, this is gonna be 1 and this is gonna be 1 as well. So it's gonna jump to 0. And then it's gonna repeat, because this is gonna be 1 for the rest of the time. So this is the function. So this function is okay, you can think of it as a strange looking thing, but it's a very reasonable dynamical system in the interval. And except for, you can think, oh, it's not so natural because it's discontinuous, but the analysis that we're going to do is a very similar one to this dynamical system here, that does this and then does that. So this, if this you think is more natural, you can think that they are very similar to each other. It goes from 0 to 1 until time 1/2, and then from 1 to 0 back again. But this one is easier to analyze, the one below. And just to give an example of why these things are actually important, I think you probably saw some simulations about the Lorentz attractor, something that does this. It's actually easier to draw than I thought. Sometimes it loops like this, and so the Lorentz attractor is something that is full of interesting results. It came with applications from meteorology, and it's a dynamical system, deterministic one. And in a PhD thesis, someone managed to prove that it has a behavior similar to this function in its center, between the two wings of the butterfly. So this is somehow what's happening inside that Lorentz attractor. Of course, it's much more complex. You know, life is a nightmare. But this is a model for something very complex somehow. So this is an interesting dynamical system. And what we're going to do is to try to see that phi is ergodic with respect to p, the uniform measure. So how are we going to see this? So it's going to be based on the decomposition we're going to do. So take some x in S. It's a point between 0 and 1. So we can think of it as 0 dot something, right? And if you write it in decimals, it's going to look something like this. But if you write it in binary, it's going to have zeros and ones. Okay. And one possible way to write this down is to say, okay, x is just the sum for I from 1 to infinity of ci 2 to the minus I. So this is a decomposition that is reflecting exactly what's above here, but there is one caveat. This decomposition is not unique, because if we take Ci to be 1 for every I, or maybe for every I bigger than 2, and C1 equals 0. So what do you have? You have 0.0111111 forever. This is actually going to converge in the sense of the series to 0.1. So it means that the composition is not unique, right? We have managed to write the same number, 1/2 actually, in two different ways. But the way to do this decomposition unique is to actually require that this does not happen. So how do we do this? We impose that the CIs have infinitely many zeros. So if you have finitely many zeros, it means that from some point on it's just 1, 1, 1, 1, 1, and that will give the effect that I just explained. So if you say Ci has infinitely many zeros, then the decomposition becomes unique. Okay, I'm not proving that this decomposition exists and is unique, just like I didn't prove that the Fourier decomposition exists and is unique, but this one is actually much easier to prove than the Fourier. So all we have to do now is understand how phi acts on these coefficients, right? That's exactly what we did in the Fourier case. We understood how phi acts on the coefficients, right? We're going to do the same here. So phi is 2x minus the integer part of 2x. So first let's understand this part. 2x is going to be just the same sum, Ci, 2 to the minus I plus 1. So this is simple, we're just multiplying all the terms that multiply the coefficients. But this can be rewritten, of course, and we can count from 0 instead and replace this thing here. So we can so this we can write, as minus I minus 1. Now here the counting starts at 0, and here the counting starts at 1. So if we sum from 0 to infinity, we get Ci plus 1, 2 to the minus I, right? So this is the same way, but we are seeing how multiplying by 2 act on the coefficients. It starts at earlier index and you sum 1 in the indices. Now what happens if we take the integer part? The integer part of a number that is decomposed as such is going to just take the minus 1 coefficient here. So in this case it's going to take, if y is decomposed as above, is a sum from I equals 0 to infinity of Ci plus 1, 2 to the minus I. This is exactly what we're going to take the integer part of. And if we assume that Ci has infinitely many zeros, then the 0 coefficient can survive, because this is just 1, but all the other coefficients combined cannot sum more than 1. So what this is saying is that the integer part of this is just C1. So we took something like this, we applied the integer part, and it became 0.1100111100. We shifted this, and now you already start to see that we are doing some shifts here, and then we possibly deleted this term. If this term appeared, it was going to be the integer part. So phi of x, which is 2x minus the integer part of 2x, is going to be the sum. We delete the first term, this, so it just starts from 1 again. Ci plus 1, 2 to the minus I. Okay, so we already understood how phi acts on these coefficients. Now we have to understand how are these coefficients distributed with respect to the uniform measure, or with the Lebesgue measure, right? I didn't say what, oh yeah, this is the Lebesgue measure. So how is the distribution of C1, C2 and so on with respect to the uniform? So let's take a look. So we have this interval 0, 1, and the first coefficient is, it measures if you are before 1/2 or after 1/2. So the distribution of Ci is delta 0 plus delta 1 over 2. Have probability 1/2 to be in the left interval, in which case C1 will be 0, and probability 1/2 to be in the right, in which case C1 is going to be 1. Now what's the distribution of C2? So C2 measures if you are in the first quarter or in the third quarter. This is what C2 measures. So C2 doesn't actually care if you are in here or in here. It's measuring if you are in here, you're 0.0 something, here 0.1 something. Here are 0.00, here 0.01, 0.10, 0.11. But the second term, C2, only looks at if you are in the first third and the first fourth or in the third fourth. So in the end, C2 also has a distribution of C1. It has probability 1/2. You have a probability 1/2 to be in this interval, in this union, and probability 1/2 not to be in this union. So C2 has the same distribution. Now, what's the joint distribution of C1 and C2? It's 1/4 to be 0, 0, 1/4 to be 0, 1, 1/4 to be 1, 0, 1/4 to be 1, 1. So it means that C1 and C2, they are distributed as delta 0 plus delta 1 over 2 times delta 0 plus delta 1 over 2. So it's a product. And you can continue this boring calculation to realize that CI's are IID with distribution delta 0 plus delta 1 over 2 under the Lebesgue measure in the interval. So this is what makes the whole calculation possible. From one hand, we know how phi acts on the coefficients, and how does it act? It's just a shift. It takes Ci to Ci plus 1. And on the other hand, we know how these coefficients are distributed with respect to the measure, the uniform measure. They are just IID Bernoullis. So in essence, phi being ergodic with respect to the uniform is equivalent by this mapping of coefficients to the shift being ergodic with respect to the product measure. So this we already proved. We know that the shift is ergodic with respect to products. So it is a a weird construction. You have to go through it a little bit more with your own hands to see, but essentially we took a dynamical system in a manifold, so to say, with a Lebesgue measure, a very decent measure on the manifold, and by mapping things on coefficients, we managed to relate its ergodicity with the ergodicity of the shift with respect to the product measure. So we got for free the ergodicity of phi. Of course, you have to finish some work here. You have to take an invariant event here and turn it into invariant event here, and of course it's going to commute. Everything here is going to commute. So I'm not giving the full proof here, but the essence is this. You can finish yourself. And now we have some interesting, some highly non-trivial examples of systems that are ergodic with respect to a measure. And now that we have many examples, next class we'll start to prove results that are valid whenever you have such an ergodic situation. See you in the next class.